Hello, everyone. I'm presenting this 2-hour lecture on uh, detector building and trajectory for the 2022 Science Olympiad season, Division C. For this event, you have to build a device that measures salt concentration in water, and the concentration will range from 0 to 5,000 particles per million. And ppm means that if you have, let's say, 1 ppm concentration, you have 1 particle of salt for 1 million particles of water. And this device will have to display the voltage and concentration to the nearest part per million, and also display an LED color based on the concentration range. So at the competition, they'll tell you if the concentration is between 0 to 1,000, display the blue LED, between 1,000 and 5,000, display the red LED. So that's what this LED stuff is about. And the next, I guess, important thing for you to know is that you'll be testing 3 different samples of water. They'll have all different concentrations, and the bottles will be 7 centimeters wide and 4 centimeters deep, so that you know how big to build your device. And to perform all of this, you'll have a total of 10 minutes, plus you'll be writing a test from the remaining hour. So this is here, you can see this drawing that I have of the sensor. The sensor here is very small. I recommend that it's larger than it's drawn here, but that's just for you to visualize. And the whole setup will look like this. So you'll have your breadboard, your sensor right here, which this is from last year. And this year's sensor will be kind of different. And you have your Arduino, which will take readings from the sensor and output stuff to the LEDs on the breadboard. Not shown here are an LCD display, which is required by the year's rules, and a laptop, which you can use to program your Arduino board. And this actually is a TI calculator, and there are some methods you can use to program this thing called the TI Innovator board with a calculator, but it's just so much easier to use a laptop. So go with an Arduino. And also one thing to note that is you're limited to 5 volts of operating power. So you can program the Arduino with a laptop during the event, but it has to run on 5-volt battery. And so in addition to building this device and actually having it measure stuff, you need to submit a design log, which shows that you have done at least 10 trials of measurement of concentration. So what you do is you take some water and you take some salt, right? And you put some salt in the water, a known amount. So you prepare a solution with a known concentration, and then you measure the voltage across this salt water electrolyte. So it is known that waters with salts conduct electricity. So if you stick 2 probes of a multimeter into that cup of water and measure the voltage between them, that's essentially the measurement that you're taking to produce a plot. Now, at the competition, you're going to do the same thing, except the concentration of this water is not known to you. So you'll have to use your previous recorded data to guess what it is. So for example, if at the competition, you get a voltage reading of, let's say, 0.75, this will be actually right here because this is a logarithmic scale. 0.75 will be about here on the plot. And so then, since you've already gathered the data for known concentration, you'll go down and find that it's roughly like 800-ish parts per million or something like that. And in the process of gathering data, you can use statistics to create a formula for going backwards from the voltage to the concentration. And this is called the regression equation. So in addition to these plots, you also need to have a labeled picture of the device and describe the functions of each component. So something similar to this picture here, we'll need to submit. You'll also need to print out the code showing the calculations and the display part. So the part of your code that does calculations and displays it, you'll need to show it to them. Now, I guess if we want to take a look at this picture, there's here actually, and this is sort of realistic to what you measure on your sensor. You look at these points, and I made two plots, one of which had both of these have the highest, or they're both linear plots, except for one of them, I set the y-intercept to be 0. So at 0 concentration, we should get 0 voltage because there aren't any salt lines to carry the current between the two electrodes. So, but there's a chat question. The other one does not look like a linear plot. They are both linear actually, because, well, look, it's mx plus b, and here's also mx plus b, but the b value is 0. Now, would you like to guess or mention in the chat which one of these two plots would you actually go for in the competition? Would you go for the one that has a 0 y-intercept, so that it assumes there is no concentration, or there's no voltage conduction when there is no salt? Or would you go with the other one? The reason why I would recommend that you choose this equation here, the one with a non-zero y-intercept, is because water itself has a non-zero conductivity. So if I take this cup of water and I stick two probes in here, sorry, if I stick these two probes in here, I will actually get a conductivity measurement, but it will be very, very small because water by itself is a poor conductor, but it's non-zero. So assuming that if there are no salt particles in this water, doesn't mean that there will not be any concentration. And this is very noticeable at low concentrations. So you should keep this in mind. So, okay, making sure, okay, we've taken care of all the chat questions. So I hope that has you thinking a little bit about the science behind all of this electrolyte stuff, why it works. Okay. Now, I mentioned there is a written test, and it will be on the following topics. Electronics and circuits, they will be interested in knowing if you know how a voltage divider works. And I don't really know why. This is in the pre-released rules, actually, so it could change. Perhaps they want you to experiment testing your sensor with a voltage divider just by hand before you move on to an electrolyte. So you can maybe you can learn about this or can read about this online, or you can ask me and I'll explain to you how voltage dividers work, but they're very simple. And then you'll also need to know how analog to digital conversion works, which is the process that takes an analog reading turns it into a digital value. And this process is employed in sensors all around in industry. So basically reading an article or two about it will help you later on perhaps as well. Then since you'll be working with LEDs on this project, so you have to have a red or a blue LED turn up for different conductivities, they're going to ask you about how do these LEDs actually work. And the real theory for how LEDs work is very complicated. It requires quantum mechanics and perhaps a bachelor's degree in electrical engineering, but maybe an article or two could hopefully do the job to give you the working knowledge that you need. But seriously, an LED, the working principle of an LED was awarded a Nobel Prize back in the day. So not that level of knowledge familiarity, but a couple of articles worth. And of course, this is an event that talks about chemistry because we're working with electrolytes. So they'll want to ask you about the effects of temperature and electrolysis on the conductivity of a saltwater solution. And you can read about this in your AP Chem textbooks, perhaps. And since this is a sensor and you need to do some data interpolation, there are going to be a couple of questions on statistics, as I've paraphrased here. So this is a very rich topic of questions, like chemistry, statistics, electronics, and this is something that frankly I'm prepared to do, but high school students, this will be a big challenge. And it will be difficult for you if you have not taken these subjects as well. So the first thing is to perhaps read ahead in the textbook so that you're familiar with all of this stuff before actually taking the build event more seriously, because otherwise you'll be kind of clueless about how to do this. And now a quick comment, the way this event will be scored is you'll be given, so the most accurate concentration wins, correct LED colors, and so these two first points are awarded based on accuracy and correctness, and the next two are awarded on completeness and also correctness. So that's that. Now, I wanted to talk about the theory behind electrolyte conductivity. And this, if this is familiar to you, then it would be a good review. And if it's not familiar, then this could be a good introduction to what you don't know, so that your further studies will be more guided. So we will talk about all of these topics in order, and they will explain how you can measure electrolyte conductivity. Now, let me describe what happens in an electrolyte. If you pour salt in water, it naturally has a tendency to dissolve, and it dissolves into the sodium ion and the chloride ion. And so imagine you're in a pool, and you see this ball of sodium and this ball of chloride, and they're floating around. Sometimes they stick together, but sometimes they also float apart because the salt dissociates. Now, the fact that these ions, there are free-flowing ions, which are units of charge, means that this saltwater solution can convey or transmit a flow of electricity. So electric current is the process of the flow of electricity or electric charge. And if you, for example, and that's why you can essentially do all of these electric measurements on electrolyte, is because there are salt ions which are free to move around in the water. So I mentioned electric current, but let's talk about what it actually means. So electric charge is a property of matter, and it's carried by a thing called an electron, which is a fundamental particle. And an electron has a unit of charge called an electronic charge. So it has one undivisible unit of charge. So you can't get half an electron's worth of charge. It's impossible. But fortunately, this unit of electronic charge is very small, so this won't present a difficulty in real life. And the unit of charge is measured in coulombs, or electronic charges, and it's denoted with the letter Q. Now, currents is the flow of electric charge. So if you imagine you have a pipe with water, and in the water you have a bunch of salt ions, positive salt ions only, or let's say even more simple, you have a pipe of oil and you have electrons in the oil. The fact that those electrons are flowing through the pipe is equivalent to a current. And the current is defined by the amount of charge that passes through some sort of point or controlled surface, divided by the amount of time that it took for this amount of charge to pass. Now, current won't flow by itself because you need to do some sort of work to push a charge from one place to the other, and in most cases. And if there's a current flowing in real life, it probably means that there's an electric potential between which the current flows. So electric potential is a measure of energy contained by a unit of charge, and it's measured in volts. And essentially, as you'll see on this picture here, if you have a high voltage, or we can compare this to waterfall. If we have a high voltage and a low voltage next to it, then electrons will tend to go from high to low voltage because they're naturally seeking the lowest energy state. Just as if you have, for example, I don't know, a bowl and a marble. If you put the marble on the edge of the bowl, it will want to roll down. And once it rolls down, it will settle down in the bowl where it has the least amount of energy in its stable equilibrium. And a similar thing happens with electric currents. So, and I guess this waterfall is an analogy to this. So current can flow between a potential difference if it's provided with a conducting path. So if I have a battery, I don't have one with me right now, no current flows between the two terminals of the battery because there is no conductor between them. The electrons can't just jump through the air because the air is a barrier. So it's a material barrier. But if you wrap a metal wire between these two terminals of the battery, then the current will flow. And the current that flows is proportional to the voltage difference between these 2 points. And that's a discovery that was made in the 19th century by George Ohm, and it's dubbed Ohm's law because the current that flows through a material is proportional to the voltage. And that's a very fundamental experimentally derived result that has been important in circuit theory and everywhere else. So this value, this constant of proportionality is called R, or the electrical resistance. Now, if you look at this cartoon here, remember we have some sort of, we have current, which is the green person here, and it's essentially being pushed through a narrow opening by this thing, and being pushed through a tube. And remember, if we have charges flowing through a tube, it's current, and it's being driven by a voltage difference. Now, if you make the tube thinner, then there'll be more resistance for this fluid to pass through. And similarly here, making the tube thinner will kind of increase the resistance to this charge flow. So that's how they've drawn Ohm as someone who ties the knot to make it thinner or less wide. And the larger the value of resistance, the more effort it takes for volt to push amp through. And essentially that confirms this statement of proportionality. And one thing to clarify, amp is ampere. It's a unit of current. So we've seen this on previous page. Amperes is defined, its units are in coulombs per second. Now, in reality, we don't have these nice pictures, or this isn't what happens when we have electricity flowing through wires, through breadboards and circuits. We don't have a person called volt pushing a person called ampere through. What actually happens is we can simplify the situation to a conduction through a simple solid or just a slab of metal. So imagine, we all know that metals are good conductors, and the reason, there are reasons for this, but let's just accept this as fact. And if we connect the 9-volt battery with one end here and another end here, we will be generating a current flow through this entire solid. But as we know, each solid, as the electron travels through the solid, it bumps into the metal particles. So there is some sort of resistance, and potential difference is required to overcome it. Now, if you try to make electricity pass through this way, it will have to pass through a longer length in a smaller area, which means there's more resistance. If you make it pass through a large area in a small length, it will pass through faster because first of all, there's less length for it to travel, and the electricity can choose more paths to go through, essentially, to put in simple terms. And now, if instead of aluminum, if we chose copper, or let's say if we chose steel of the same size, steel has a higher resistance, and that's a material property than aluminum. So there is also a material constant, the value rho. And from this, we can, with common sense, derive this equation for resistance. I've mentioned that we have the value rho because when electrons travel through a piece of metal, they actually bump into the metal ions here. And when you zoom into a piece of metal in a microscope, you'll see that they're actually structured like a crystal. So we have atoms in a nice orderly arrangement, just as you see with the red circles here. And the reason why these electrons are traveling is because we apply a voltage difference between the two ends of the metal slab. And this voltage difference generates an electric field, E, which pushes the electrons through the slab. And this E is here, electric field. However, so if we increase the voltage, there will be essentially more of a pushing force to push the electrons through. And that means the electrons will travel through the metal faster. And if we go with a metal that has a lower resistance, then the electrons will bump into these into the crystal lattice less, so then it can flow through faster as well. And just to reiterate, the relationship between the speed at which electrons flow through is governed by mu, which is called ion mobility, or in some places called ion mobility. This is a material property. It depends on what material you have. So for example, if we have rubber, which is well known to be an insulator, there will be a very low ion mobility because the rubber grabs onto the electrons and it doesn't allow for electron flow. Now, even within metals have different crystal structures. And if the crystal structure is arranged more compactly, then it will be harder for electrons to pass through. So that's how different metals can have different resistance values. Now, well, we're getting there. We understand. We'll soon understand why all of this term electron mobility is very important to us when looking at electrolytes. But before then, I wanted to explain or connect to you how electron mobility fits in with the bigger picture of current and voltage difference. So really, at the microscopic level, this should say microscopic, we have imagined a tube, a wire, a very thick wire or a wire through which electrons flow under the influence of a voltage, just as we have in this picture here. And we want to really get into the microscopic details because when we're going to talk about electrolytes, we'll have concentration. We're essentially designing the conducting solid from scratch when we're working with electrolytes. So that's why we need to take a microscopic approach here. Instead of treating the electrolyte as a bulk solid with a constant material property, we recognize that the more concentrated an electrolyte is, the more charge carriers there are, and hence the greater the conductivity. So that's why it's important to do all of these microscopic considerations here so that we can predict the value of the electrolyte's conductivity from physics and chemistry before we even start measuring. So this is going to be a tough explanation, but I will read out all of the points and you can pause and return to this later if you're still confused. So imagine we have a wire and we have electrons in it represented by blue dots. And we choose an arbitrary volume cross-section of the wire. Let's say this red cylinder here. And we know that if we apply a voltage, then electrons will flow through with a certain velocity. And this is represented with this letter V. And this velocity is equal to mu times E. Now, what are the number of electrons in this red volume? Is very simple. We calculate, first of all, the cylinder, the area of this volume of the cylinder is the area times the distance. And the number of electrons, in turn, is the concentration of electrons multiplied by the volume. So the number of electrons will be A times D times N, where A and Z are the volume, and N is the number of electrolytes or electrons per unit of volume. So now we know what is the number of electrons in this volume here. Now, we don't really care about electrons. In fact, if you have charge carriers in your electrolyte that have +2 and -2 ionic charges, then you will actually have to adjust this by a scale factor of 2. But let's assume now that we have electrons here, and then if we know the number of electrons, the amount of charge in this red volume is this number multiplied by E, which is the charge of one electron. So that should be straightforward. Now, we already know that these electrons are traveling through the solid at a speed of V, but this also means that this volume or the amount of electrons or the amount of charge inside of that red volume will enter this wire in the same amount of time it takes for an electron to pass from one end to the other end of this volume, and that is time. That time value is the distance divided by the velocity. So you can imagine that if you have a pipe and electrons are entering this pipe, and you're just passing in a cylinder of electrons, this red cylinder here, with a certain velocity, the amount of time it will take for that cylinder of charges to enter will be the length of that cylinder divided by the velocity. So that's straightforward. But look at what we have done here. We know the amount of charge in this cylinder, and we also know the amount of time that it takes for it to travel through. So we know delta Q and delta T, which means we now know the current, I. So if we now grab our formulas and pull them all in one place together, we can see that the current I, in terms of the microscopic values, is the area of the wire times the number of electrons per unit volume times electronic charge times mu times electric field E. Okay, well, that's great, but it's a bit useless. But remember that we were assuming that these electrons are moving through given a known value of voltage. So we apply a voltage to both ends, and we ask these electrons to move through. So if we want to find the resistance, which is what we're going for in the first place, we will need to divide that initial voltage by the current that we calculated, given the assumption that we have a voltage V applied to enter the metal slab here. So if we find a resistance, it pans out. So we have a couple of cancellations. We cancel electric field. And if we want to draw your attention here, we get this following line at the very end. We have this quantity times D over A, which looks very similar to the formula we saw just earlier, rho times D over A. So let me remind you of that formula. It is here. So exactly this formula. So we got the same thing, except now we know that rho is actually this quantity here. Now, since we know that sigma is defined as 1 over rho, then we know that sigma is equal to this quantity, which n times times mu, where n is the number of electrons per unit volume, E is the charge of one electron or the charge of one charge carrier, and mu is the ion mobility. So congratulations, we now know how to predict, since n depends on the concentration and mu is a constant, electrolyte constant, which depends on the temperature and the solute. We now know how to predict conductivity. Voila. So we don't even have to do this event. We can just, grab up our pens and papers but wait a second, we don't know what the concentration is. What we do know is that we can measure sigma, and if we put these two variables on the other side, we can determine n, and from there we can determine the concentration of the solute, of the solution. So just to reiterate, you'll need to you'll need to go search online what is the value of mu for a salt water concentration, and this value depends on temperature. So I advise you to your detector building for this year also include a small temperature probe. So you'll have to build on your device from last year if you have one, and measure the temperature and use that to correct for and determine mu. And these mu values are available in they're just books with pages and pages of numbers, and it's called data that people have gathered experimentally. And you can kind of hard code those into your Arduino and then reference them when you measure stuff. I'll quickly finish off with what materials and supplies you'll need for this. So this is a very so this event doesn't require you to buy too many supplies other than, an Arduino, a screen, a couple of lighting emitting diodes, breadboard wires, the battery. So it's basic electronic components. And these tend to be cheap because they're small and they're mass produced. So yeah, you can buy these at a website called DigiKey or Adafruit. And if I could venture, I will show you a demo of how a DigiKey works, because if you recall, I had shown a demo of McMaster Car, which is a website which you can use to buy any piece of hardware you'd like. So you can do the same thing with electronic components. So this is DigiKey, and let's say I want to buy a resistor. So we type that in, and we have a bunch of options here. There are several ones that we need to keep in mind. Chip mount or surface mount resistors is not what we're looking for. That's what they have in CPUs and PCB boards. So we want something called a through-hole resistor. And if you're not sure what this thing means, just copy this Google image and see if this is what you're looking for. So, and the way you know what you need to look for is if you watch a bunch of YouTube videos, you'll kind of see what people use to make things work, and you should aim to get the same thing. Now, so here we are. We have all sorts of resistors, but we don't need any resistor. We want, let's say, 1 kilo ohm of resistor, or so we can type in here in this resistance box. What value of resistance are we interested in? So we want something between 1 and 10 kilo ohms, so that we can power our LEDs from a 5-volt battery without burning them. And let's see, I guess we could select active power, and there are a couple of other things. So one thing here is we have power watts, the amount of power that these resistors could handle. So if you choose something that's 0.05 watts, it's going to be super, super tiny. And it's not enough it's basically not the scale that you're working at. You should go down to something like half a watt, that's good. Quarter watt is good. I guess let's do quarter watt. And so as we apply the filters, we have less options remaining, and that's good because we don't want to choose between 100,000 options, 99% of which are useless. You want to choose between 1% of options, which maybe represent 10 different alternatives that we can realistically buy. And so let's say we want 2 kilo ohms because, okay, we like the number 2. So we can select this, but they have so many different numbers here. So apply filter. And now we actually go here and look through. And, well, we can click one of these buttons. I don't know, let's click this one. Oh, this is kind of interesting. They're selling one for $4.50. That's kind of a ripoff. So we can sort these by price. Oh, they have one for $28. Horrible. So let's just do reverse sort. And notice how they're selling one for less than a cent. But the problem is that the minimum order you have to buy is like 5,000. So we're obviously we don't need 5,000 resistors. So we can apply a filter here. And let's say, yeah, so this looks like a good one. It's 10 cents per resistor, which is reasonable. And we only need to buy one, so that's cool. And so we can click on it, and we can, now, as we click on this thing, so we have a resistor. A resistor is a relatively simple electronic component. But in the future, you could be also buying transistors, LEDs, reactors, all sorts of things, and they're complicated. So to help you navigate exactly how this thing works, all electronic components have included a thing called a data sheet, which I've mentioned previously. So this is the piece of paper that tells you everything about this resistor or electronic component, how it works, basically what currents and voltages can it handle, etc. And so we have here, we have the dimensions, which is useful. So if we're, for example, designing a PCB, we need to know how big this thing is, because if it won't fit, we can't buy it. We need to get something else. So we have here these dimensions. And we have a little other parameters. So maximum overload voltage is 300 volts. That's great. So for the stuff, we only need 5 volts to be happy. So this is good. So it won't burn out on us. And it will operate fine in a very large temperature range. So that's good. And blah, blah, blah. There are more kind of stuff. It's also noted that this thing is like lead-free, which is, I guess, maybe a bonus, but either way. So once we're satisfied that this is the type of resistor that will work well for our applications, we can, of course, buy it. And, the price goes down the more you buy it. So that's cool. And, you might be tempted to just buy one of each resistor, but that's a very bad idea, because you might need like more than one, or you might want to have freedom to experiment. So it's much more easier if you have a kit of resistors. Like, I don't know, you can go to eBay, for example, and Google Arduino or resistor kit, and you'll get like a huge bag of resistors and other stuff that will be handy. So that you don't, and you'll save yourself a bunch of time. It might cost like $30, but it's kind of worth your money. So you see I have a huge string of resistors and a bunch of other goodies. And basically means I don't have to go out and look for them by myself. So get a kit. There are people who have put some thought into what will be convenience and how to save you time. So might as well take advantage of it and pay like maybe $1 or $2 extra. Okay, so that was DigiKey. There's another website called Adafruit, which is where you can buy Arduinos and electronic components. And these people like cool, I don't know, displays, like whatever, lots of LEDs, little scientific value. But nonetheless, they have like, you can get like, I don't know, maybe an LCD display from them, and maybe also an Arduino. And these people have a lot of very good things. Like they also have buttons. So it's very user-friendly. And so you might as well give them, try looking things out. Well, they also have kits and projects good. So those are the two websites I recommend you start searching to buy stuff. Because if you just go on Google, you'll get a bunch of garbage, which paid to be advertised on the first on the list of searches, and it won't always be good. So I have given you this recommendation because it took me some time to find them as well. All right, now maybe you'll need a lot of fancy materials, but the tools you'll need are very simple. You'll only need a laptop, maybe a soldering iron and soldering flux, and scissors and pliers. Basically, the type of stuff you need to like work with any electronics thingy, a small one. We're not talking about power electronics because that requires huge currents and voltages. This is very small and tame. So this is all the tools you'll need.